Welcome to the Deep Dive.
Hello.
Today we are strapping in for one of the most intellectually jarring rides in all of physics.
Oh, yeah.
Chapter 15 of Feynman's lectures. We're facing the profound, unavoidable reality of the special theory of relativity.
It really is a mind bender.
Our mission today is basically to distill this chapter, get a step-by-step summary of how physics changed forever.
Right, because for nearly 2 centuries, Newton's laws seemed perfect. They held the universe together.
Exactly. But we know those laws ultimately revealed a deep, fundamental inconsistency, especially when you look at something as seemingly simple as light. So we need a quick but, thorough understanding of why classical physics broke down and what radical new architecture replaced it.
And we're leaning on Feynman's explanations here. Very visual, very intuitive.
Yeah, I mean, think about the shock of that moment. Physics was working, describing orbits, cannonballs, everything.
And then a tiny experimental observation starts to unravel the whole thing.
It forced the entire framework of time and space to, well, collapse.
And what's fascinating here is how universal that collapse was. This isn't just like a minor tweak to a calculation.
No, it's a complete restructuring of reality.
This chapter fundamentally alters how we even define mass, time, energy, even distance.
Yeah.
We have to move away from this comfortable assumption that time ticks identically for everyone, everywhere.
That idea of absolute time, gone.
Gone. Replaced by a model where measurements are fluid, linked, and utterly dependent on how you're moving relative to what you're observing.
Okay, so let's start where classical physics started getting it right. The principle of relativity.
Right, the foundation. Feynman emphasizes this. The laws of physics look the same in all systems moving uniformly in a straight line.
That's the key. Uniformly, no acceleration.
Yes. And the classic analogy is the spaceship, right? If you're sealed inside a ship moving at a constant velocity, it doesn't matter how fast, you could do any experiment inside, toss a ball, measure gravity, time a spring.
And you'd have no way to tell if you were moving at 1,000,000 miles an hour or just sitting still.
Exactly. The results must be identical. And this was supposed to hold for all laws: mechanics, electricity, magnetism, everything.
Okay, but even before Einstein really tied it all together, there was already a wrinkle emerging in classical mechanics itself, wasn't there?
There was. The original Newtonian definition of force, F dmv to dt, well,
Yeah.
it needed a tweak.
Right.
Early observations of very fast particles, like electrons, showed that their mass seemed to increase with velocity.
So mass wasn't constant.
Apparently not. Even before relativity fully formed, physicists realized that this inertial mass, m, depended on the Rex mass, m0, and this strange factor.
One with the square root.
Yeah, 1 over the square root of 1 minus v squared over c squared, that denominator.
The Lorentz factor, we'll be hearing a lot about that.
We will. It's basically the speed penalty. If your velocity v is tiny compared to c, the speed of light, that factor is basically 1.
And Newton's laws work perfectly.
Perfectly. But for fast stuff, that discovery hinted that motion, well, it costs mass somehow.
Okay, let's unpack this more, because the real driver of the revolution wasn't just mechanics acting weirdly. It was the collision with electromagnetism.
Right. Maxwell's equations.
The simple Galilean transformation was the sort of common sense math that worked fine for everyday speeds, XEST, and the key part.
It just assumed time was absolute, the same for everyone.
Yeah, and that assumption failed spectacularly when you applied it to light.
It did. Take the classic paradox Feynman mentions, the car and the headlight.
Okay.
If you're in a car moving at speed and you turn on the headlights, common sense, Galilean thinking, says someone on the roadside should see that light moving at c plus u.
You just add the speeds. Seems obvious.
Seems obvious, but it's wrong. Because Maxwell's equations, which were experimentally confirmed, insisted that the speed of light, c, is a fundamental constant.
Same for everyone, no matter how the source or the observer is moving.
It cannot be c plus u.
So there's the conflict.
That's the fundamental conflict. If c is constant for everyone, then that simple Galilean math, which relies on absolute time and space, it must be wrong.
The constancy of c basically forces the structure of space and time themselves to change.
Or the principle of relativity, that the laws are the same for everyone, would just fall apart.
Okay, so physics needed a fix. A mathematical fix that could handle both the weirdness in mechanics and keep the speed of light constant.
And that solution was the Lorentz transformation.
Which Lorentz himself derived first, right? Then Poincaré and Einstein used it.
That's right. And the really, really mind-bending part is that these new equations, they don't just transform space, the x-coordinate.
Like transform time, too.
Yeah.
There's a t that's different from t.
Time is no longer absolute. That's the key insight Einstein cemented.
So the Lorentz transformation basically acts like a mathematical guarantee.
You could say that. When you apply it, both Maxwell's laws and the modified laws of mechanics stay the same between reference frames.
It saves the principle of relativity.
It does. But the price is abandoning absolute space and absolute time.
Okay, now here's where it gets really interesting, experimentally. The proof that sort of forced physicists to accept this bizarre new reality.
You mean the Michelson-Morley experiment? 1887.
Right. Before Einstein, the idea was that light needed something to travel through, this invisible medium.
The ether. Like sound needs air.
So they built this clever device, an interferometer. Could you describe that simply?
Sure. Imagine splitting a beam of light. Send one half along a path parallel to the Earth's supposed motion through this ether.
Okay.
Send the other half on a path perpendicular to that motion, then bring the two beams back together.
And the idea was the light going upstream and downstream in the ether wind should take a different amount of time than the light going cross-stream.
Exactly. You'd expect to see a shift in the interference pattern when you recombine the beams. That would reveal the ether wind. They found nothing. Zero. No shift, no difference in travel time, no matter how they oriented the apparatus or when they did the experiment.
That null result was just devastating for the ether theory.
Utterly. It was the crucial physical evidence. And the only way to explain why there was no difference
was if the apparatus itself was somehow changing.
Precisely. The conclusion was that the arm of the interferometer pointing in the direction of motion must have physically contracted.
By how much?
By exactly that Lorentz factor, the square root thing. The math predicted this contraction was necessary to make the light travel times equal.
So the experiment didn't just fail to find the ether. It accidentally confirmed that space itself physically shortens in the direction of motion.
That was the interpretation that fit. Motion warps space.
Wow. Okay, so let's talk about the consequences for us, for observers. The first big one is time dilation.
Yes. Feynman uses that great thought experiment, the light clock.
Right.
Describe that.
Imagine two mirrors facing each other. A pulse of light bounces between them, up, down, up, down. Each round trip is one tick of the clock.
Simple enough. Now, put this clock on a moving spaceship. If you're on the ship, you see the light go straight up and down between the mirrors. But if I'm standing outside watching the ship whiz by, I don't see the light going straight up and down.
Why not?
Because the mirrors are moving. The light pulse leaves the bottom mirror, but by the time it reaches the top mirror, that mirror has moved forward.
So the light has to travel a diagonal path.
Exactly. A zigzag path. Longer than the straight up and down path seen by the person on the ship.
But wait, the speed of light has to be the same for both of us. That's the rule.
That's the rule. So if the outside observer sees the light travel a longer distance, but at the same speed,
I must take more time.
It must take more time. The external observer must see the clock on the moving ship ticking slower.
By how much slower?
By that same Lorentz factor again. 1 over the square root of 1 minus v squared over c squared.
So clocks in motion genuinely run slower than stationary clocks.
Yes. And this isn't just a theoretical quirk. We see it constantly. High-speed particles like muons created way up in the atmosphere.
Yeah.
They have a known, incredibly short lifespan, fractions of a second. Based on that, they shouldn't have enough time to reach the Earth's surface before decaying.
But they do.
They do. Because they're traveling near the speed of light, their internal clock is running much slower from our perspective on Earth. Their lifetime gets dilated.
So they live long enough in our frame of reference to make the journey.
It's direct proof. Their clock is running slow relative to ours.
Okay, hang on. If time dilation is real, physically real,
Yeah.
does that mean if I, took a super fast spaceship journey and came back,
Yes.
would I actually be younger than my twin who stayed home? Or is it just how they measure my time?
No, it's absolutely physical. You would genuinely have aged less.
Whoa.
For you, on the ship, your clock ticks normally, your body ages normally in your frame. But compared to the stay-at-home twin, less time has passed for you. Time is a physical dimension that literally stretches and shrinks with speed.
That is profoundly weird.
Okay.
So the corresponding effect is Lorentz contraction. This relates back to Michelson-Morley.
It does. It's the other side of the coin. If an object is moving, its length in the direction of motion appears shorter to a stationary observer.
Compared to its length when it's at rest, its rest length.
Right. And it's shorter by that same square root factor, but this time it's multiplying the length. L equals L0 times the square root.
So time dilates, gets longer by 1 over the factor. Length contracts, gets shorter by the factor itself.
Exactly. You can't have one without the other. It's this contraction that explains the null result of Michelson-Morley, the apparatus arm shrinking, canceled the expected time difference.
And this combination, time slowing, length shrinking, it leads to another fundamental shift, right? The idea of simultaneity.
Yes, this is crucial. Things that look simultaneous in one reference frame are not simultaneous in another frame that's moving relative to the first.
Can you give an example?
Feynman uses one like this. Imagine trying to synchronize two clocks at opposite ends of a very long, fast-moving train. Maybe you flash a light from the exact middle. For someone on the train, the light reaches both clocks at the same time. They're synchronized. Simultaneous.
Makes sense.
But for someone standing on the platform watching the train go by, they see the light signal traveling towards the back of the train, which is moving towards the signal, and towards the front of the train, which is moving away from the signal.
Ah, so the light hits the back clock first.
Correct. From the platform observer's point of view, the clocks are not synchronized. The event at the back happens before the event at the front.
So simultaneity isn't absolute. It depends on who's looking.
Exactly. It's relative. Another piece of common sense bites the dust.
Okay, so finally, let's circle back to mechanics. How did momentum have to change? Relativistic dynamics.
Right. To keep momentum conservation working properly under Lorentz transformations, the definition had to become P equals m times v, but where m is that relativistic mass.
The mass that increases with velocity.
Yeah.
M equals m0 over the square root factor.
That's the one. And this mathematical change has a huge physical consequence.
Which is?
It explains why nothing with mass can reach the speed of light. As your velocity v gets closer and closer to c.
That square root in the denominator gets closer and closer to 0.
Right. So the mass m heads towards infinity.
Meaning you'd need an infinite force to accelerate it any further.
Which is impossible. Particle accelerators see this every single day. Electrons pushed near light speed become thousands of times heavier than their rest mass.
Just because they're moving fast.
Just because they're moving fast. You need
Yeah.
enormous amounts of energy just to keep them going, let alone speed them up more.
And this relationship, this link between the energy you put in and the resulting increase in mass, this leads directly to the grand finale.
The most famous equation in science.
The equivalence of mass and energy.
Yes. Feynman shows how analyzing the kinetic energy needed to increase a body's relativistic mass leads straight to EMC2.
What does that equation really mean?
It means the total energy E of a body is its relativistic mass m times the speed of light squared, c2. This total energy includes two parts. There's the energy it has just by existing, its rest energy, which is its rest mass ml0 times c2, and then there's its kinetic energy, the energy of motion, which accounts for the increase in mass above the rest mass.
So energy and mass are interchangeable, two sides of the same coin.
Essentially, yes. If you have any process, chemical, nuclear, whatever, where some mass disappears, a little bit of mass, delta M.
That mass isn't really gone.
It's not gone. It's been converted directly into energy according to delta E equals delta M times C squared.
And because c squared is such a gigantic number.
A tiny amount of lost mass releases a huge amount of energy. Think of nuclear reactions, an atomic bomb, or even just TNT exploding, though that's chemical, the principle holds.
The energy comes from a minuscule loss of mass.
Exactly. EMC2 is the conversion rate.
Mind blown. Okay, let's try to wrap this up.
So, to summarize this whole deep dive, special relativity basically throws out the old, comfortable ideas of absolute time and absolute space.
Yeah, the classical view just didn't work.
It replaces them with this single, unified thing, spacetime. And because the speed of light is the one universal constant,
Everything else becomes relative.
right, our measurements of distance, of time duration, even of mass and energy, they're all interconnected and they all depend on how we're moving relative to what we're observing.
So what this means for us, diving into Feynman, it shows the universe is just way, way stranger than our everyday intuition suggests. Even the most solid-seeming laws of physics had to bend or break when faced with this weird fact about light speed.
It forced a revolution.
Okay, so here's a final provocative thought for you, the listener, something Feynman brings up right at the end of the chapter.
the four vectors.
Yeah. If distance measurements and time measurements are relative, the only thing that stays the same for all observers is this combined quantity, the interval in spacetime.
Which behaves mathematically like a length.
Right. Feynman introduces these four vectors, basically taking the three space coordinates, x, y, z, and adding time as a fourth coordinate.
And the amazing thing is, these four component vectors transform under Lorentz transformations.
In exactly the same way that regular 3D vectors rotate in space.
It implies space and time are truly blended.
So think about how that forces us to reconsider what a vector even represents, not just an arrow pointing in physical space.
But maybe an arrow pointing in the very fabric of space-time itself.
Something to chew on. Thanks for joining us on the Deep Dive.
See you next time.